So we finalized that little homeostasis side. What we can do today, I think we could go into at least initiate a portion of the immune system. I think a part of the, by the way, Janet, where is going to be the labs for?
342.
342 next week. Macmillan 342 and lab coat.
And closed-toed shoes.
Yeah, like flip-flops. So those will be the times we're gonna the quiz will be there. Well, I think what we can. I don't know if you can do this. You know, there's one of the classes on lactation, salmon migration that I wanted to.
The case studies.
Yeah, because then should I leave that to you guys to discuss, or you prefer to? Or you have already? Okay, that's fine. So then they have a plan. So we're gonna go over those homeostases, a little later, because I just wanted to really start this part, because then next week we're gonna have labs, then the next week classes, and then the other week, after the next week, and then I'm gonna stay out, and we're gonna have another week of labs, and one other week is going to be either classes, we can review stuff, or we can even have like one of those weeks to start setting up some of the presentations for you. I'm thinking what would be the best, but I want to push some of the material now, so we go over. So we finish off at least the first portion, and now we start going over. It's not the pathological side, but we start to go over some of that. The system that we're going to start explaining today is the immune system, and again, the immune system is already this bridge between what we're going to do. The stress physiology already is the start of the pathological processes and how we're going to modify things. But the immune system is this system that is, to begin with, extremely cool. It is like one of the most interesting systems in your body. It doesn't have one specific, obviously, it has specific organs where some of those cells are produced and matured and so on, but it doesn't have this vital sort of function as the other systems that we saw so far have. Okay, so if all of a sudden we are in a very sterile state or environment, and we have no immune system, you'll be okay. You can live in a bubble, with ultra-filtered air, ultra-filtered water, no way for you to get infected by anything. You will go on. Okay? Now, the whole thing is that the immune system was one of those things, there's always those nice, enormous questions about, where the immune system came from, how did it evolve? And this is one very, very interesting thing. Because the immune system is the system that can, and is actually one of the few systems where your cells, aside from cancer, can overreact to yourself. Okay, so you can have autoimmune diseases. You cannot have autocardiac disease. There's no way for you to attack yourself unless it is from an immune cell or immune system standpoint. So the importance is obvious. Anytime you're exposed to a foreign molecule, which could be part of an organism, a microorganism, or a toxin, or something else, your immune system is responsible to defend your organism against that. Now, in the process of defending, you have to understand that your immune system is circulating around you, regularly, producing, turning over cells, having new cells, younger cells going over. And before we go into what how the subsystems may work, which we're going to go in a little more detail, it is for you guys to think about the notion of what is self and what is non-self. And what is self and non-self doesn't necessarily have to do with being a pathogen molecule or not. You know, because if I transfer my liver to any of you, it's going to be rejected. Meaning, there is a certain combination of molecules inside of each of our cells that is really recognized by our own immune system. And this immune system, which is very, let's say, is a very private immune system, recognizes what is yours and tries to make the differentiation and attack what is not. Either what is not yours or what it looks abnormal. Okay, so this is, and I think this definition of what looks abnormal is even more complete, because when you have cancerous cells, normally you, as we are right now, probably there are some cell inside of us that is not multiplying right. But we are able, the immune system is able to go there, identify, and kill the cell, so it doesn't become a cancer. Okay, so it's not necessarily a foreign body or something, it's just abnormal. Okay. For that, so let's go. If you have to defend yourself, so this notion of self, we're going to talk quite a bit, but there's two large systems or subsystems inside of the immune system, which is the innate and the adaptive immune system. Most of the vertebrates, they have both. Most of the invertebrates, they basically have only the innate. And you can say that one, you would say that is a more general immune system. The other one is a more adaptive or acquired immune system. So one, you're basically born with it, and there is very low specificity. Meaning, you have to be born with a set, your immune system, with a certain knowledge of what is self and non-self. No, you're not going to, your immune system doesn't have to learn from the get-go, like everything. So it's going to learn what is self and non-self just like after you're born. You would be crazy, like that wouldn't work. How that was acquired? Evolution. Millions of years of evolution. Okay? So you do have a set, or for example, sets or parts of your actually DNA, long, like very, very complex parts of your chromosomes that are just responsible, or they have been evolved to have or to produce certain kinds of receptors in your cells that recognize a wide variety of what antigen is. And when I say antigen, certain things, think from a biochemical point of view, or think from a normal cell function point of view. There are certain things that it really doesn't matter where it comes from. It is a threat, and it is abnormal. It doesn't have to be learned. Now, when it comes to other things, and this innate is normally a fast response, early phase response. It can be both molecular and cellular, and is very non-specific, not super specific. It's more of a general response. When it comes to the adaptive immune system, this is the one that, you know, has this big influence of what we call T cells, you know, and they tend to be a little bit more delayed. I'm sorry here for typos, customized, you know, kind of response. So basically meaning it has to be very, very specific to something. In that case, that you have to have been pre-exposed to. So it's not something that you were born with, that set of, that toolkit that can, you know, basically kill everything. This is something that is very specific to it. So as an example, if you talk about certain types of toxins that comes from certain types of bacteria, this is, you don't have to learn that. body already knows that that bacteria produces something that is not good. It doesn't necessarily goes well with your body. Already knows it is bad for you. Your innate immune system tends to get rid of it. Now, if it is the new strain of flu that is coming this year, your body doesn't yet know that. It is a very small variation of the influenza virus, and all of a sudden it can catch you off guard, and eventually you start, become sick of that thing because you have never been pre-exposed to it. Okay? Now, we're going to talk about some types of these cells. So let's say you do have this ability to recognize what is self and non-self. And we do talk about this, what we call, it's very common, is a lot of how you recognize those things is through a series of receptors. Okay? So receptors they can be receptors, or they can be, for the most part, these receptors, they have to be in the membrane of cells. Some of those receptors, they are in every cell in your body. Okay? And some of those receptors, they are in just the specialized cells in your body. So some of these, for example, cell surface receptor. This is pattern recognition receptor, and this is major histocompatibility complex. Okay, these two things are probably, they're not the only ones, but they're probably the ones that cover a bunch of how you recognize what is self and non-self, and how you trigger a certain immune response. So cells, then, once they bind to some of those and they recognize as, for example, non-self, they promote, a cellular response and also a humoral response. When I say humoral response, is like cytokines, chemokines, antibodies, everything that is a molecule that can be produced by some of the cells, you call them, humorous response. Cytological response is when you have the actual cell going there, and for the most part, they kill something by engulfing and killing and so on. And then obviously you have this antimicrobial effector mechanism. So if you really think about this, and we can try to spend some time, it is something like this. Your cells. So all of your cells, basically speaking, you're going to have, let's say this is a cell of your body, like a regular cell. This is a cell of, for example, a pathogen, a bacteria. Okay. And let's say this is some of your immune cells. Okay. You're going to see, and this is why the idea of having receptors, let's put receptors like this. Yeah, okay. Very, very nice little receptors. So why? Because lots of the recognition of self, non-self, they have to be done by contact. Okay? So you don't have something just floating around with no contact with other cells, either cells from your body or cells from like somatic cells that are non-immune system or only immune system, is not going to necessarily cause a reaction or an inflammatory or even a disease. But that doesn't happen. You know, any cell, anything that is foreign and eventually gets inside of you, it immediately get in contact with something. Okay? So the thing is, eventually, this cell here that is yours, not a regular cell, that's what a regular cell is. Non-pathological cell. It is, the body has a way to say something like this. Listen, this is almost like, you know, you have to think of these receptors like almost what it is an ID. You know, a police officer stops you, you know, on the road, and the first thing that he asks is your ID. Why? Because then you can go inside this car, check your ID, and say, yeah, you're a good person, okay? Or it can go back and maybe say, yeah, it's Janet's ID. And all of a sudden she has a list of things that she did when she was a teenager. You know, she drank like crazy, she was, you know, all sorts of fights, and all of a sudden they're like, oops, there's something wrong with Janet is a cell. Okay? So eventually, so basically speaking, the regular cell, they have ways to base these receptors. What they do is like they get a sample of what's inside and show here. So this guy here eventually can come and say, oh, identify this little thing that it was shown from this regular cell and say, oh, you're okay. So some of the cells of the defense cells in your body are always doing that. It's always like touching everything. They go around, it's funny, like, you know, they go around touching everything, all of your cells. So eventually, they might go here and say, oh, the pathogen cell is you know, is here, you know, sunglasses, you know, very sneaky. And then it goes, nice, I think I'm gonna go through like I'm a regular cell. But they come here and they show their sample. Once this guy come here, they say, it's like Janet. Okay? Now you have a sample or ID that doesn't belong. Okay? And then you can do several things. These immune cells, there are several types of cells that do this. And through different kinds of receptors. Some are these PRRs, some is major histocompatibility complex. Generally speaking, for example, major histocompatibility complex of the class 1, it is almost expressed in almost every cell you have. It's your ID. You know, they have to show some of that. They also have, and they also show some of these, you know, these cells here, this is normally major histocompatibility class 2, which is normally like T cells only. You know, so these T cells, it is part of some of your adaptive immune system. Then you do have also some other cells, like for example, cells that are less, such as neutrophils, macrophages. We're going to go over all of those. That also have, you know, some other. So this is a little bit more specific. This here is a little bit more general. But the idea is that they both can recognize stuff that is foreign and kill it. So this one here, pathogen recognition receptors, is almost this first line of defense. So how your neutrophil go around, you know, you're going to see that the neutrophil, I think the next slide is going to be on the innate immune system. And the innate immune system goes all the way from physical barriers and chemical barriers. When I say chemical barriers is what? Your stomach with a pH of 2. It is a chemical barrier for pathogens. It kills a bunch of stuff. Your small intestine, that your pH goes to super basic. It's a chemical. Your skin, the barrier. Okay? sweat, tears can be also barriers. You know, the way all the ciliary or all the humidity kind of, the way the shape of your, upper respiratory tract to trap dust and stuff, and actually some of the microorganisms, that's all part of your innate immune system. So you have mucus, ciliated cells, physical flushing such as, tears. You have the urinary tract, just the fact that, is a unidirectional flow, that you pee and there's no way in. This is one of the ways to actually get rid of infection. If you drink a lot of water, actually means that you're less likely to have, for example, bladder infection, urinary bladder infection. Why? Because you're flushing things. Another way is like vomiting, diarrhea. You are removing things. This is all somewhat part of your innate immune system. So the other one, it goes into the types of cells. Neutrophils, eosinophils. The other one is basophil, monocytes, macrophages. The stuff is like, these are all part of what we call your white blood cells. Okay? Your white blood cells is your defense cell. Okay, this is no surprise to all of you. But each of them, they have somewhat of a function. Since this is the innate immune system, let's say they tend to have some of what we call this pathogen pathway recognition receptors. Okay, sorry. These are the ones that go around and say, oh, they communicate with, especially they try to go with, your pathogens around, and if they find something, they don't necessarily go to every cell, but they try to, recognize each of them, or anything that is foreign, it tries to recognize. What is the difference between some of these white blood cells? And you might have some of that in some of the clinical cases. The difference is when you see white blood cells and why your leukogram, when you go to the doctor and you go to do a blood test and you have a leukogram with the differences in types of cells, is because each of them, they can be, for example, an indication of a specific problem. For example, eosinophils, they tend to be very high once you have parasites inside of you. It's the way the body works. It tends to be the best cell to agglutinate into parasites and get rid of. Neutrophils tends to be really like, if you really want to talk about your regular soldier, is the neutrophils. He attacks everything. Okay? It doesn't matter. He attacks everything. Basophil tends to be, for example, associated with sometimes not wanted, allergic reactions. Okay, so this is the other stuff that, sometimes that's the part when you start attacking yourself, for some reason, or you attack something in a way that you cannot stop. You're going to see, especially during the stress physiology response, is that as important as triggering inflammation is to stop inflammation. Because you will see that, your immune system, to begin with, is very energy costly. It costs a lot of energy to run it well. The second part is, eventually, if that inflammation continues to go on, you will start damaging your own body instead of just microorganisms. So people always talk about the pro-inflammatory side, but it's as important as the pro-inflammatory side is the anti-inflammatory side of it. Okay. Monocytes. Monocytes is just this precursor cell, and the importance here is that it is going to be or it's going to give rise. It's almost like they are produced, you know, in the body, and they circulate for a few days, and then they spread through the organs. Then you're going to see, like, you know, if you go to histology classes, you're going to go to each organ, and each organ, like you have Langerhans cells in the skin, you have Kupffer cells in the liver, you have one of the pneumocytes in the lungs, and these are all monocytes that then infiltrate into the organs, and they differentiate into something. And this differentiation into something is just is almost like a defense cell that is embedded into the organs, so they can. These are the cells that I told you are like sometimes touching everybody, and going over and trying to make sure that, you know, or not necessarily touching everybody, but as soon as you have something that is not belong there, it is the first one to identify. And the other part is that this macrophages in this is here is called dendritic cells. Dendritic cells. I think in the other slide I have that set. This is actually described. These are cells that, you know, we're going to later going to be able to talk, and we call them antigen-presenting cells. And antigen-presenting cells, they are going to be important for, these are the cells that bridge the innate with the adaptive immune system. Okay? Eventually, you have all this fight going on, for example, with the innate system, but eventually some cells will have to, oh, let's say this is a new thing, and you have to have a very fast response to it, or you would like to have a more specific response to a certain pathogen. These cells are the ones that will eventually going to say, hey, I look at this pathogen here, or some of these cells. Sometimes, you know, you're going to have these macrophages or dendritic cells. Sometimes it's not necessarily, actually these cells here are, let's say dendritic cells here. They recognize, for example, that this guy here doesn't belong, and it is a new threat. Well, first of all, it's going to try to kill this thing. But the second part is that this guy here will also try to take this molecule here and present to somebody else. In this case, the somebody else tends to be the T cell. Sorry. They can both do, but this is what, let's say, this is the regular pathway that it goes. The thing is, this is the guy that will coordinate all the, for example, antibody production, or cells that can, for example, cells that can not necessarily will produce antibodies, but they will actually kill, cellularly will kill the other, these other pathogens. But, you know, at this point, this guy was going to coordinate a reaction that will kill only this. How important that is. And you say, yeah, that looks like a rational thing to do. You know, it's a general, let's say it's a general reaction first, followed by a more adaptive, specific response. And this has a lot to do, in the case of immune system, it has a lot to do with timing. Why? Because most of the time, the timing is going to be important. Okay? The reason why some people, for example, get, like if you have gotten the shot for flu this season, and let's say this year they got it right, okay? And the vaccine really protects against the strain that they think is going to be coming up this year. Because this is how it is with flu. Flu is kind of a weird. The reason why is that you have been pre-exposed to it. That's the reason, that's the whole thing with vaccination. Vaccination doesn't necessarily make, functionally speaking, your immune system more able or less able to combat something. It is just going to make your system faster. Okay, so the reason why somebody got sick and somebody didn't get sick is because your system was faster. Simple. Lots of this stuff in terms of pathological, it has to do with how much infection you got, which basically is the amount of virus, the amount of bacteria that you got, and the amount of defense or how fast your defense was able to go with. Okay, so these macrophages and dendritic cells, so put it back. So these are two very important cells. Neutrophils, you can put it there like the soldier. These two are really the spies. Like these two are really important for a very, very specific response. So they tend to be called like the macrophage sentinel cells because they, as I told you before, the monocytes leave the bloodstream, go to the organs, and they stay there. You know, eventually they turn over, but then more monocytes go inside, and they are always there. Okay, and they tend to be, or they can have phagocyte, like they can phagocyte other things, but their major function, among others, is to actually present this antigen to T cells. This is the other, so I'm talking about this in a certain way. At the end, when we finish, I hope I will be clear enough to describe a little bit more detail of this inflammatory reaction. We're going to have another, I think under pathology, we're going to talk only about inflammation, which is nothing less than just this at a more systemic scale. Okay, so once you, how this is, for example, associated with inflammation. All of this, once this thing starts, either unspecific or specific response, inflammation is going on. Okay? So when I say inflammation, what are some of the signs of inflammation, for example? Redness, edema, pain, loss of function, you know? So you have some of those cardinal signs of inflammation, which has a lot to do with what? Not in general. Most of the time, you're going to have what? You're going to have a certain spot in your body that will be attacked. Sorry. So it's not that it's rare, but it is rare. You're not going to have like infection or inflammation in your whole body. You may feel fever, which is kind of systemic. You may feel not well, dizzy, whatever. You have systemic effect. But the thing is, you're always going to have infection, probably at first, initially. You're going to have somewhere specific. Okay? And that's the part where you're going to have what we call inflammation. And for that to happen, all of these cells, imagine some of these cells are in the tissue, some of these cells are in the bloodstream, but during inflammation, they make something, they make certain changes in that local of, where it is inflamed, where you have to bring more cells. You have to bring more cells to attack that antigen as fast as possible. If it is the lungs, it is the lungs. If it is a cut in your skin, then it's in your skin. If it is something that happened in the heart or the urinary system, wherever it is, you're going to have a flood of cells, and with that, liquid and other things leaving the bloodstream into the site. So that's more or less where this falls within, inflammation. So this dendritic cells is what we call professional antigen-presenting cells. Macrophages, they do a lot, but they also have phagocytic activity, so they can actually kill some of those pathogens. Dendritic cells, no, they do nothing else. The only thing they do is get some of these cells from, or some of these molecules from the pathogen, process, and try to look for some of these other officers, such as the T cell, and present those receptors there. In this case, they have major histocompatibility complex 2 receptors to those T cells. So basically, they are this link between innate and adaptive. Macrophages and dendritic cells are the only cells that the T cell recognizes. Okay? That's how important they are. The T cells then will go on. Do you remember, I think, maybe if you have read some of the other stuff in immunology, you can classify some of those lymphocytes. Lymphocytes is B cells, T cells, they fall into this lymphocyte category. But I don't know if you have heard, especially if you have read something on HIV/AIDS, because that's where lots of the development on immune system came from, is, CD4 plus, CD8 plus. These are just, and they have CD whatever, like they have all kinds of, these are receptors. These are specific receptors that some of these T cells have. So you identify, when they do studies, like hardcore studies on the immune system, they try to identify what kind of cell that is, okay, so they can track. The other part is like, and you should try to understand, like these guys here, one of the things that they try to do as well on this adaptive system is that they can go on and say, okay, so I recognize this guy, and now I know exactly how to get to him. Then this guy here can go on and transform into a, what we call like cytotoxic T cell. Or they can go on and transform into a B cell. And then will go on to transform into a plasma cell. These guys here produce antibodies. These guys here basically come here and chew this guy up, like and swallow this guy up. So they start to divert into a very cellular or humoral response. Okay. Now, during this process of going and becoming or inducing a B cell here specific to a plasma cell, or inducing a certain cytotoxic T cell, this is, and I'm sure you have heard about this before, this is where clonal expansion occurs. I don't know if you have heard about this term, but clonal expansion has a lot to do with the speed by which you're going to fight a certain pathogen. Let's say you have this very bad flu, and you have this influenza with a very specific strain, and you have never been exposed, so you're going to get a week or so bad. Okay? Because it's going to attack your lungs, it's going to attack a bunch of other things, especially upper respiratory tract, and you're going to feel miserable. Now, imagine that you have been pre-exposed, and you already have this cell here ready to attack your influenza, your flu. This guy here, what it starts to do, they start to multiply like crazy, like very fast. Very, very, very fast. And you basically make what? Clones. Clones. Lots. They multiply. That's why, and that's where the immune system, for example, consumes a lot of energy. And then all of a sudden, you have many cells, and these cells, when I say specific, they are just specific for that strain of flu, of influenza. That's why it is so, what's the next question you could ask? Ronaldo, does that mean that do I have some of these T cells with specific, we call epitopes, but this little thing from the this little protein here from either from a regular cell or for a pathogen cell, we call this little thing an epitope, which is where you're going to make your reaction against. Do you have little cells with those processed things for every antigen I have ever been exposed to? Imagine that. No, the reason why we don't get like polio, we don't get measles anymore, we don't get all these things because we got vaccinated, and eventually I am 100% sure we have been exposed to some of this bacteria or viruses, but we never get sick. Why? Because we can very fast, if in case we get some stupid family that didn't vaccinate their kids and they have all this, they start spreading some of these bugs around. If we have been exposed, we can all of a sudden fight. Okay? So does that mean that your body somehow has some of these T cells over there floating around your body, but specific for those? Do you think that happens? But think about, like I told you, like 3 diseases. Imagine everything that you have ever been exposed to. Dust, pollen, whatever the heck you want to, like everything. Molecules in general. Do you think you have all that? You do. You do like have thousands and thousands of those that can be activated quickly. Because in order for you to have this guy here ready to become this or to stimulate these cells, it takes a while. Okay? And sometimes in those cases of infection, a few days, that's it. That's enough for you to, germs will be spreading at exponential rate. Those 2-3 days are enough for you to get sick. So your immune system will take a little while until it catches up. And that's the beauty of this system. One of the most remarkable systems you will have. So these dendritic cells are these amazing cells that will then try to, bridge this, present those guys to T cells. Some of these T cells, in books you can maybe refer to some of these T cells that have never been activated by anything. You call them naive T cells. These naive T cells can then become something that is like, oh no, I'm going to be a measles T cell. And you're going to be there. Hey, I'm here. They multiply here and there, but they don't go through clone or expansion if you're not exposed to. But if one day you need to, bang, you expand like crazy and you fight very fast. Okay? Yes?
So the virus changes every once in a while, right?
Yeah.
So we get it every year. But what about like measles or polio?
Yeah, the thing with influenza, which is this virus that causes flu to us, is that it is high. It changes at an incredible rate. So this little guy here, this little protein here, changes every year. Because when I say the protein, think about what is exactly that you're trying to do. Like you're trying to, what the hell you're trying to process that will make you more likely to fight against that agent? Generally speaking, what you need to have is something that can bind your cells, your defense cells, to the pathogen. And when I say binding, it really is surface. Because cells in general, if they don't have something that makes them bind to each other, what they do, even because of charge, they tend to repel each other. They don't like to be that close to each other if it's not forced physically, or if there isn't something there to actually breach that repulsion and make them go together. So what they have is, for example, antibodies. What does antibody do? What do you think they do? They basically act as a receptor. So they go and these B cells, these plasma cells here, they produce like gazillion antibodies. IgG, immunoglobulin G, this is probably the most known of them ones they produce. And they go here and they bind all these guys. Once they bind, your defense cells can recognize this. So they come here and they bind to this cell and they eat. They eat the pathogen. Okay, so this is what it is. Your receptors and antibodies in this case, what they increase is binding capacity. So they can bind to each other, they can kill. They can bind to the pathogen and kill. Very good. So this natural killer cells, and this is still, so far we already started talking about the adaptive, okay? But imagine you do some of those things here. Through this cell here is a little different receptor. It just goes to this guy and eats. No antibody production, no specificity, just this guy coming here. Oh, I recognize you. You're an old friend. I know who you are. Kill. So one of the cells we can call, like, you do have some of the neutrophils doing that. You have some of the macrophages doing that. You have some of the basophils doing that. But then you have also some of these what you call like natural or natural killer cells. These natural killer cells, they are slightly different because these cells, what they end up doing is trying to, for example, natural killer cells tend to kill lots of tumor cells. Okay. So they can go to actually, especially some of these, this is a regular cell, right? And this I was talking, this is a pathogen. But imagine that you have a regular cell that is a cancer cell. So they don't necessarily, you see some of these receptors, they just recognize pathogens or T cells. But you're going to have some cells that can come here and actually kill this cell here. So if it is a cancer cell or a cell that has been infected with a virus, what is the difference between, what is something that a cancer cell and a viral or a cell with a virus inside is different than the pathogen? Well, your pathogen really has like everything inside of that cell is different. The membranes, everything. Cancer cell, it's your own cell going crazy. A viral cell, still your own cell, but being infected intracellularly. So they require a slightly different cell to go there because they can go there and check these cells. In general, these natural killer cells, they are one of the few that recognize this histocompatibility class 1. So your cancer cells or your cells with a virus, once they present this thing here, they say, yeah, you're one of us, but you're super weird. You're kind of crazy. I don't like you. I'm going to kill you. This is what the natural killer cell does. Okay? It is different, and they like to do like this killer, sometimes they call this cytotoxic T cell or killer T cell. It's not the same. These ones here will go and do a little bit different of an effect. But you see, it is super coordinated. It has different cells that do different things. Where does this, for example, fall into, for example, the next class of stress physiology, or when it comes to treatment and so on. Treatments, when it comes to the pathogen, you can do stuff that kill this guy. For the most part, something that can be specific. Now we're starting to have more specific stuff, but before it was more like general recommendations. You try to fortify this, and you try to weaken this. Okay? How can you kill that guy? Antibiotics, so on. Or if it is a virus there, antiviral drugs. During inflammation, you have all these things going, and these cells here, they're consuming a lot of energy, and sometimes you can reach a point where you deplete lots of your cells. So lately, for example, lots of therapies on as an immune booster can be applied. Fight, for example, this one here, I was talking like the natural killer cell. They come here. Lots of development on this side of boosting the immunity against cancerous cells have been done. Okay, so now you're starting to think on how I can actually or effectively, kill this thing. Now, these guys, or the next one is going to this part. Yeah, we went on immune, proteins, phagocytes, antipathogens, natural killer cells, unable to identify subtle strains, no memory. So I think for this slide, this is obviously the most important part. So no memory and no specificity to subtleties. Okay. Some of these parts here, yeah, this is how they can kill stuff. I said that, phagocytosis, or coming here, some of these cells come here, they normally, no antibody, just kill it, eat it. Okay. Another way to do it is what we call this complement system. We're not going to go in detail, but some of these, they can produce or they can release certain molecules that poke holes into this guy. This is what the complement system does. But it's still kind of non-specific. Okay? Still on the non-specificity. And they are obviously good when you have this like too large or too numerous pathogens. The greatest advantage for this is that for a lot of things, you don't need to necessarily activate your adaptive system. You can just send your Marines there, and then they get rid of the infection. Go.
So how does the body trigger the innate compared to the adaptive? So
the innate is triggered by the pathogen. Okay? So, or in the case of an autoimmune disease, it is something that all of a sudden is then perceived as not yours, and then you can have a reaction to yourself. Okay? And on the adaptive side will only happen once that pathogen is recognized as new. Once that thing is recognized as new, then you're going to go into the adaptive system to create a more specific set of reactions from the immune system. And then both will act together, trying to get rid of it. Okay? Good?
So the adaptive wouldn't automatically be triggered in the beginning? That would be like...
Not necessarily. Yeah, it would be more of a delayed. It's a delayed response, correct. Pretty good. So all of this, I told you, like I mentioned, I ended up mixing all the, innate with the adaptive. But eventually here, an antigen will actually induce a new antigen. Your memory. Very good. So So the whole thing is that it will, the specificity, of course, will be a lot higher, a lot greater. You will create immunological memory, which is the floating around of T cells that have that information, you know, to attack a certain molecule from a very specific antigen, a very specific organism or toxin or so on. Now, the adaptive system, we always talk about these B and T cells, okay? B and T cell receptors, and they say the B and T cell receptors to recognize these guys, you can have as many as your body has been exposed to during your life that is perceived as foreign. Okay? So you can have lots of them. Lots of them. So, lots of memory. If you really think about this, isn't it remarkable that the body can do that? It is just crazy that the body can even recognize after I was vaccinated, when I was for certain things at a very early age, and they still have that memory and try to recognize some of these organisms. We talk about the B and T cell clonal expansion. And that thing, in a nutshell, summarizes what we're trying to do. It's a summary, but you see how much blob is there? It's a lot of things. The most important thing is it's not that you go too crazy, but the same way that we went to some of the reactions in the kidney, some of the things in the lungs, pressure, if you don't have that global view, it doesn't really matter if you know the super specific receptor that somebody did a research on. You're not going to be able to put things together. That was my concern when I put this class together, to be integrative physiology. I cannot go too deep into each of the systems, but it requires you to think about the bigger picture of it. And sometimes this is exactly what you miss in some more specific classes. You go a little, what is major histocompatibility? And then people start going, major histocompatibility complex is a cross-section of the chromosome 6 that goes there, and you have the epitopes, and the receptors are these, and that, and you're like, before you go there, go to this, okay? So some of these immunological memory, specificity, antigen, epitope, clonal expansion, B and T cells. If you feel like you don't, this should be enough for us to go through the course. But if you're really curious about some of these things and you don't necessarily have full knowledge, go back, read about it. It's always good. You're always going to gain some more knowledge. It's going to improve how you view all of that. Okay? So the B and T cells, as I mentioned before, is almost like the T cells. You have one of the slides in the end of this presentation. They're like, you have T cells that are cytotoxic. You have T cells that are killer cells. You have T cells that are regulators. You have T cells that are just, they just go to B cells to then make that B cell produce antibodies. So it's the T cell tends to be this, much more even than the B cell, this central cell from the adaptive immune system. No wonder HIV attacks this guy. Of all cells in the body, HIV attacks one type of T cell that really does that bridge. So what you do, especially before, when you didn't have all these drugs that we have today, you basically kill your whole adaptive immune system. You get done with a lot of cytological, humoral response, and you die from a flu. HIV doesn't necessarily kill you. But what kills you is any other thing that you get. Including the fact that you can die from a flu, and actually one of the things that you die a lot from when you have HIV, from cancer. Because you end up killing a big portion of the immune or the surveillance system of your body. Okay? So it's a very sneaky virus as well. And another virus that changes like crazy. That's why super hard, or have been almost impossible to create vaccines up to this point. Okay? Okay, so for example, this is a very, very just illustrative. Once you have antigen, this is the stuff of primary, secondary immune response during vaccination. You have your humoral response. And when I say humoral response, if I have to ask you, okay, from a vaccination, tell me what happens to your immune system. And this thing here just illustrates that, why sometimes you have to have, when you have 2 or 3 doses, or you have to, for certain diseases, you have to give it annually or every 10 years or the stuff, is because maybe your immunological response for some of these vaccines are not as good, or it is a time where that vaccine that you took a long time ago no longer affects the new strain that is coming out. Whatever the case is, I'm not a specialist, I'm not an expert on this, but you see that, your first response tends to be smaller for many or almost all the vaccines, and the second one tends to be, so this is one type of immunoglobulin, one type of antibody. This is a different type of antibody. It's the same. You see, you have this Y-shaped kind of molecule. The only thing is that the body tends to have, like, sometimes IgA. Some of these humoral responses are not even only specific to it. You have lots of immunoglobulins, for example, in the mucosa, and they attack basically everything. So sometimes they are tied together like one next to the other. Sometimes they are in kind of a star shape. Sometimes they are just themselves. It is just the way they do in order to be a bit more effective. So what you end up doing is you inject this antigen A. The second time when you inject it again is almost a month later. You have a much greater and a much faster response. This is just to give you this sense of speed. So if you are infected here, look how long it took for you to have like 15 days. This other one, less than a week, you have this kind of response. Enough for you to get rid of the certain infections.
Is there a probability that the immune cells don't come in contact with the pathogen if the vaccine might be taken?
So is there a possibility that the immune cells do not get in touch with the vaccine? I think it's almost impossible unless you don't have an immune system. Because once you inject that, and you can give that, sometimes the antigen can be given, depending on the vaccine. It can be orally, it can be intranasal, it can be obviously intramuscle, subcutaneous, whatever that is going to get in touch with some mucosa of yours, is going to get in touch with the bloodstream, or is going to be injected in the muscle. Whatever that is, it's very unlikely that no cell in your body on the defense system won't get in touch with it. So the vaccine then, it is basically this guy here digested. It is already somewhat they found a way to get the part of the bacteria or the virus or whatever that promotes the inflammatory reaction. They tend to modify or process in a way that doesn't necessarily induce the disease, but induce the immune response. It's almost like they trick the immune system, okay, in order to have that. But I would say very unlikely.
So for example, like our pets, when we bring them for like vaccinations,
Yeah.
If the adaptive immune system has that memory, then how come they have to get boosters every year?
So yeah, that's the thing. I think, depending on the vaccine, and I think when I say depending on the vaccine, it has two things. Either the molecule, the epitope that you're trying to mimic from that vaccine is not very stable, and you end up having to repeat. Or the strain modifies with a certain frequency, which tends not to be the case because they don't develop vaccines every year. Aside from flu that I know, I might be speaking a big, stupid thing, but I don't think most of the other vaccines, they have to be redeveloped every time, because it's very costly to do that. I think flu is one of those that it is just really there's no other way. They modify so bad, and you probably have heard about, the vaccine this year didn't work. Oops, wrong strain, sorry. So they almost try to put a bunch of strains together in the vaccine. But it is mostly because for whatever reason, and let's give more like this general answer. I think for whatever reason, either the body doesn't maintain those cells floating for too long, because maybe whatever reason doesn't perceive as being so bad, or the strain modify. But it's a good question. Actually, it's a very good question. Because there's several types of vaccines. Some of them you take once in your life. Some of them you have to take every so long. Some of them you take every year. So it's a good point. Almost there. Okay, so the other one is basically this thing, you have these T cells, several types of T cells, and then several ways in which you can basically kill. So these killer cells tend to affect not only the natural killer cells, but also the cytotoxic killer cells, T cells. They go to those cells that are like either cancer cells, or they also have or viral inside. Some of the other types, you don't have to, this, I'm not gonna ask you specifically on this, but they go all the way from killing stuff to regulating stuff. So if you go into hardcore books of immunology, you're gonna say, freaking Ronaldo told me that, T cells are gonna kill everything, and all of a sudden you have this other guy there. And the stuff is the same way that this guy promotes this like super duper strong response against something, comes back to the other point. This system have to stop at some point. This is the reason why naturally the body starts to produce cortisol during disease. It is triggered by stress. So once you are sick, or you go through struggle of the sickness and stuff, you get stressed, you do have cortisol going up. And cortisol is your natural, for example, anti-inflammatory. And people very commonly ask, why are you producing anti-inflammatories eventually? And sometimes maybe you're still fighting those guys. And it is tricky and it is complicated because the body has to go to a very fine balance. You cannot go with this forever. At the same time, you want to kill the pathogen. But at the same time, you don't want to weaken this before it kills everything. But you have to stop, otherwise this is going to kill you, this kind of response. So this is the type of thing that, it has to be controlled by very, very fine tuning. Oh yeah. The next 2 or 3 slides, the next couple of slides is basically talking about some of this communication between cells. they call it here cytokines, and sometimes they call chemokines. But the whole thing is something like this. Once, I talked about, how this can promote innate or an adaptive, or how these cells here, either these or these here, can go and fight tumoral cells. All of this, every time I put like an arrow or a line, what am I doing? I am communicating things, okay? And some of the stuff is like this. In order for you, for example, to say, I want to induce this cell and then I'm going to try to freaking expand, clonal expansion. How do I induce other cells to do this? How do I go about, one, as I said before, is touching, is cell-to-cell contact. The second one is by releasing these molecules. Some of them, most of them, are produced by those cells in the innate or the adaptive. So neutrophils, basophils, eosinophils, but T cells and B cells, they also produce those. So the idea is that cytokines is basically the communication. It's almost like the microphone of these cells. It's how they communicate with each other and how they, for example, can make others differentiate into a certain type of cell they want, or to aggregate more cells into a site. So if the inflammation, as I said, in the liver, you're going to try to do everything that all the cells in the blood that are white blood cells, eventually they migrate to the liver. Okay? Interleukins, very, very, very common. Several types of interleukins exist. Most notably, you talk about pro-inflammatory interleukins or pro-inflammatory cytokines. So the same way that all of this go, you remember that T regulatory cell, they also might produce cytokines that are anti-inflammatory. So you try to do this in different ways. So you say interleukin 1, interleukin 6, tumoral necrosis factor. These are all types of interleukins in general that they are considered pro-inflammatory. They are going to promote like a little bit of vasodilation. They're going to make white blood cells go from the bloodstream to the tissue. They're going to make some of these T cells or these antigen-presenting cells to differentiate or to make the inflammation or the immune response faster. At the same time, you're going to have other types of communication, or like interleukin 10. Interleukin 10, you don't need to know those things, but just giving the example. It's one type of cytokine that tends to be considered anti-inflammatory. Okay? Interferons. So some of you remember interferon as a molecule for maternal recognition of pregnancy in the 312 class, but this is a classic antiviral cytokine. Okay, so it's one that is produced by some of the for example, natural killer cells that tends to aggregate more cells and tends to have an antiviral effect. Very good. The next one is the same. When I say chemokines, it's just a different name that is given. So they have different kinds like CCl, CXCl. So these are types of chemokines that do just the same. At the end of the day, we're not going to go into the specificity of all of those. But when you hear interferon, interleukin, tumoral necrosis factor, this is central to how the immune system works and how they communicate with each other. Does that make sense? Nice. So once I return the week after, so next week is going to be lots of labs. Week after, we finalize the stress response, and then we're probably going to start already the pathology. So we're going to go from immune, stress, and the initiation. And then probably we're going to have a couple of things on inflammation, and then specific injuries to the tissue. I think we're going to have a pretty good follow-up then up until we finalize the course. Okay? Thank you very much. See you next week. Go ahead, sorry.